So, dear colleagues, today is the first our seminar in this year, and our special guest today, Professor Roald Hoffman, who was born in Ukraine, by the way, in Zolochiv, Lviv Oblast, but that time it was Poland, and was named in honor of the Norwegian explorer Roald Amundsen. During the Second World War, his family was taken to the Nazi ghetto and later to the labor camp. After the war, they moved to Poland, then lived in camps in Germany and Austria, and in 1949 finally settled in the United States. He received his Bachelor of Arts degree in Columbia University and earned his Master of Arts degree in 1960 from Harvard University. Then he obtained his Doctor on Philosophy degree from Harvard University in 1962 while working under joint supervision of Martin Guterman and subsequent Nobel Prize winner William Lipscomb. In 1965, he went to Cornell University and remained there, where he is a professor emeritus now. Hoffman's research and interests have been in electronic structure of stable and unstable molecules and in the study of transition state interactions. He has investigated the structure and reactivity of both organic and inorganic molecules and examined problems of organometallic and solid-state chemistry. Hoffman has developed semi-empirical and non-empirical computational tools and methods such as an extended Huckel method, which he proposed in 1963 for determining molecular orbitals. With Robert Woodward, he developed the Woodward-Hoffman rules for elucidating reaction mechanisms and their stereochemistry. For this work, he received in 1981 Nobel Prize in Chemistry, sharing it with Japanese chemist Kenichi Fukui. In his Nobel lecture, Hoffman introduced the isolabel analogy for predicting the bonding properties of organometallic compounds. Some of Hoffman's most interesting work examines bonding in matter under extreme high pressure. In 2017, a Roald Hoffman postage stamp was issued in Ukraine. And dear Professor Hoffman, the microphone is yours. You can start your lecture.
Yes, thank you, my friends in Kharkiv and everywhere. It's a pleasure to talk to you. I just remarked at the beginning that this is one of those days where the temperature, and I mean the weather, is colder in Ithaca at -9 than it is in Kharkiv. This does not happen that often. Anyway, our climate is actually quite similar in a number of ways. Yes, I want to talk to you about some chemical work. The things I will talk to you about they are not in general, as you will see, a part of the education of chemists. And yet my lecture is very much directed toward chemists, as you will see. The reason that these things are not part of the education of chemists, or many of the more advanced things are not, is that some of the experiments are very, very difficult to do. They involve very high pressure, as you'll see, and the experimental facilities are available at only a few places around the world. But underlying these are structural and bonding considerations that are, of course, universal. So here is the title, The Chemical Imagination at Work in Very Tight Places. I will justify every word of this title, what I mean by chemical imagination, which may seem rather vague at this point. And the very tight places will become clear, and it's just a way of saying high pressure. This is work done in the last 10 years of my active scientific life, working with a physicist, Neil Ashcroft, who was an expert in this field. He died 2 years ago, and but the work could not have been done. It was a very fruitful collaboration, which enlarged both his experience and my own. So let's talk about pressure first. Everyone knows about pressure. We have taught students the ideal gas law, PV equals nRT, the equation of state. We have all pumped up the tire of our bicycles or cars. The pressures involved in a bicycle or car tire are not very large compared to the pressures that I will talk to you about. I'm going to use a common unit of pressure in the high pressure community, which is a gigapascal. And 1 gigapascal is approximately 10,000 atmospheres. Now, I'll come back to this pressure at the center of the Earth, but I want to say first is that, of course, chemists know what high pressure is good for. It's in part what makes the Haber-Bosch process the most successful industrial process in the world. Let me put it to you in a biochemical way. In your bodies, half of the nitrogen atoms in all the nitrogen-containing molecules in our bodies, they have seen the inside of a Haber-Bosch factory. That's how successful this process is. The rest have come through a normal biological fixation. But if you remember, and we use it as an example to teach students about the effect of pressure on the equilibrium of this reaction, N2 plus 3H2 to 2NH3, that there is a reduction in volume, and therefore it'll proceed in a certain direction if you apply pressure. We know that the pressure is used, but the pressure is 130 to 300 atmospheres in a typical, all over the world, this is being done routinely. You can buy a reactor that'll work at that pressure. It's not a problem. But that is not what the kind of pressure that we're talking about. The kind of pressure we're talking about is the kind of pressure which is at the center of the Earth. And that is 3.5 million atmospheres, or about 350 gigapascals. That is a typical pressure in which some of the experiments I will tell you about go on. And at such pressures, our intuition, which is based on bicycle tires and car tires and atmospheric pressure, doesn't work very far. But yet some physical principles do work very far. Just to tell you what happens at such a pressure, at a pressure of 3.5 million atmospheres, the volume of a chunk of solid lithium or methane or water or benzene, it decreases for lithium or methane by a factor of 5, the volume of the chunk. Water by, meaning ice, by 3, and hard metals like soft metals, iron, gold, metal decrease by a factor of 1.7 in volume when you apply that pressure. So things are really squeezed together. Now, what made all this possible is that the development of an experimental device over the years, but especially about 30, 40 years ago, called the diamond anvil cell, which has, as you see at upper left, 2 diamonds, and they are squeezed together through a hole in a metal plate, and when they are squeezed together in a device which you can hold in your hand, not very big, that can be placed into a larger hydraulic press, and you can obtain pressures of 1 to 3 million atmospheres in that device. And now the diamond allows you to some measurements you can do, in particular in situ crystallography, single crystallography, but it is a certain kind of crystallography where you have no control over growing the diamond and orienting it in the way that you want to orient it. The crystals form in there under pressure, and you have an interesting question about how to measure the pressure. I can tell you about it, but there are also larger diamond cells, as you see one at upper right, about 0.5 meter across. There are also multi-anvil cells, and a second experimental entry into the field happens through the high pressure that is generated in a shock wave. For instance, a spacecraft you see here at left, one of the American spacecraft, the shock wave it sets up as it re-enters the atmosphere. You can also set it up in some of the current experiments that have to do with fusion. You can reach pressures, again, of a few million atmospheres or higher, and you can do some measurements there. The thing about the laser heating, which is part of what is the current fusion experiments, is that not only does the pressure rise, but the temperature rises. So you have to deal with that. And whereas in the diamond anvil cell, you can control the temperature, and you can actually heat. You can heat in there with a laser also. You can do certain spectroscopies. You can do infrared and Raman spectroscopy. We're back to the diamond anvil cell. Inside the diamond anvil cell, in situ, you can do Raman spectroscopy. You do some UV spectroscopy, it's not very useful. You cannot do NMR. It just cannot do it in there. You can measure the conductivity. There are limited spectroscopies, and a lot of the advances are going to come from being able to do other spectroscopies. So what happens when you compress matter? When you compress matter, this is not even high school chemistry. This is just what our practical experience with balloons. There is only one imperative for matter under increased pressure. It has to decrease its volume for a constant amount of matter. And when you decrease your volume on a microscopic scale, the only thing that you can do is to get the atoms or molecules closer to each other. It's not that they have a choice. They have to do it. You are making them do it and compelling them to do it. So one of the more obvious things is that materials which are more dense, if there are two materials which are identical in chemical composition and one is more dense than the other, an example is diamond and graphite. Graphite is only about 2/3 of the density of diamond in carbon atoms. They're both carbon atoms. There is no question about what will happen under pressure. Graphite will convert into diamond. Will it convert into? It will not convert into gem quality diamonds, but it will convert into some form of diamond. And there are interesting ways of growing crystals out of this. It would be nice also to do it at lower temperatures. So just a few gigapascals that is a few, 100,000 atmospheres will convert graphite into diamond just well. The other thing that is obvious that you know about is gases convert to liquids to solids. The average distance in a gas between atoms, like in the oxygen, nitrogen molecules of the air, the average distance is about 10 times the size of a molecule. And so that's a lot of empty space. It's not empty. They're attracting each other weakly. That's why they condense. But if you compress, you hasten that condensations, and gases convert to liquids to solids. You know that through liquefied natural gas and solid carbon dioxide, dry ice. The next thing that happens does involve a little bit of physics, and that is that because the molecules are squeezed together, as the pressure increases, they interact more with each other. That means that filled levels spread into a band, unfilled levels spread into a band, and sooner or later they will cross each other. And what you'll get is what happens in general is that virtually all materials become metallic under sufficiently high pressure. But the question is how high that pressure. There are some very interesting stories that have appeared in the last 20 years, and that is some materials like metallic lithium and sodium, which all of us know what they look like, especially sodium. These are metallic at low pressure, but as you compress them, they actually become insulating. But then eventually you compress them more, they return to metallicity again. To see metallic sodium, which every one of us has seen, to see it in a diamond anvil cell become transparent, because that's what it does, and insulating, but then return to metallicity, that is a very striking sight, which is one of the features of doing high pressure work. There is a landscape of chemistry under high pressure. Xenon and iodine. Xenon can be made solid under pressure, of course. Iodine is solid to begin with. Under pressure, these have been metallized. That is, they can be compressed, and the solid xenon becomes metallic, and solid iodine also becomes metallic. And there's an interesting question, does it become monoatomic? But probably not when it becomes atomic. The other rare gases and the other halogens have not been metallized so far, meaning radon, meaning argon, they have not been, and neon, they have not been metallized. Neither have been chlorine or bromine, but at least xenon and iodine have been metallized. There is a variety of structures, and we'll see the reasons for that. One of these things that happens that's interesting is that if your students ask you why is CO2 so different from SiO2, one thing you can tell them is if you apply pressure, CO2 becomes like SiO2. That is, under high pressure, only 50 gigapascals. That's 500,000 atmospheres. CO2 goes into a quartz-like structure. And nitrogen, diatomic nitrogen gas, a very strong triple bond in a molecule, goes into a 3-coordinate framework, which is similar but not identical to the frameworks of phosphoric and arsenic at about 1 million atmospheres and at high pressure. Remarkable things. You get unusual stoichiometry. So, and this is also something where you can tell a difference between chemists and physicists. it turns out that you can take a mixture of sodium chloride, rock salt, and chlorine gas, and you subject it to pressure, and people have found under from different mixtures compositions which you see at the top. Don't pay any attention to the structures here. Just look at the compositions. You can get Na3Cl and you can get NaCl3. Okay, you're going to ask the obvious question. What happens when you recover these to ambient pressure? These are at high pressure. At ambient pressure, they go back to NaCl plus Cl2. You cannot maintain these at ambient pressure. That's another question. What can you do that's synthetically useful in the sense of making something at high pressure and recovering the strange material? But it's interesting by itself that you can make Na3Cl and NaCl3. And at the end of this lecture, I'm going to ask you as a chemist, what you think is the structure of Na3Cl and NaCl3, and what intuition as a chemist, not as a physicist, you can bring to what structures these might have. So we'll talk about that. Let's talk about the simplest, metallic hydrogen. Metallic hydrogen has interested people from 1935 when Wigner and Huntington said it was metallic. They knew H goes to H2, but what they did was they estimated if you kept it as hydrogen atoms, would it become metallic at high pressure? Of course it would become metallic. And then that has been the subject of discussion and controversy over time. And the hydrogen has been made metallic at high pressures, but only also at high temperatures. This is by Nellis. It's the lowest article here. It is where Neil Ashcroft comes into the picture with he's my collaborator on the physics side, and he came into the picture from the beginning on this. In fact, I'm going to tell you a little bit about our entry in this story. Neil Ashcroft knew that, and so did all these other people who worked on hydrogen, that the hydrogen atoms would collapse to H2 molecules before the gas of hydrogen atoms or the solid of hydrogen atoms would become metallic. And then Neil Ashcroft had a primitive idea that maybe you could do something like chemical precompression. Maybe you could distract the hydrogen atoms. I'm using anthropomorphic language on purpose. Could you distract the hydrogen atoms by throwing in some additional atoms, and they might form chemical bonds to those atoms, and to keep them from and in the process to get them close to each other. I would like you to calculate sometime for yourself how close the two non-bonded hydrogen atoms are in methane. You can do this with high school trigonometry. And if you do that, you will find that the two hydrogen atoms in methane are closer together by far than the van der Waals contact of two hydrogen atoms in H2. So there is something interesting. The hydrogen atoms in methane have, by bonding with a carbon, been brought from the viewpoint of the hydrogen atoms, you can think that they've been brought closer together. He wanted to exploit this idea, and we helped him in this by looking at some things. One of the things you could ask as an inorganic chemist is, what is the most hydrogen-rich material? What is the most hydrogen-rich inorganic compound that I know? So I told him, the most hydrogen-rich compound I know is K2ReH9, which has in it ReH9 2- ions in it. And maybe that might be a good thing. Well, it doesn't lead to metallic hydrogen. But these studies about hydrogen-rich systems have led to some of the most exciting results in recent physics studies. And these are the Eramet studies. Eramet's just passed away recently, on a mixture of H2S and H2, which can give SH3 material, which is superconducting at 203 Kelvin, as you see. And also Hemley group and Eramet's group have made a lanthanum H10, which is superconducting at almost room temperature, 260 K. There's also some terrible story of some unscientifically bad results, which have claimed higher superconductivity, which have clouded the area, but that's another story. Both of these materials that you see here, which are well established and to some extent reproducible. There's another interesting story we could talk about. How reproducible do you judge a scientific result if there are only 2 laboratories in the world who can do the experiments on it? That's the situation in high pressure research. Even then, there are other complications. Anyway, this SH3 and LaH10, they cannot be recovered to room temperature. But if they are superconducting, gives the hope that you might make something which is recoverable. Here is a review article that Wojtek Grochala and Neil Ashcroft and I.N.G. Feng, who is now in China, have written about the chemical imagination with the title of this talk. And we, at high pressure, I could tell you more about this. But what I want to do is I want to give you a way of thinking about this, which summarizes a lot of things. It does not predict a given compound, but which gives you a general way to think, which we have gained from a lot of looking at structures. So here is a hierarchy of responses to pressure by matter, molecular and extended under high pressure. And these are things which increase which happen, but these are not exclusive. It's not that the first thing happened and then the second. There's overlap. These are rough things. But the first thing that happens when you compress things can be summarized in 2 ways. It can be said as penetrating the repulsive region of intermolecular potentials. I'll illustrate this for you in a moment. And the other way of saying it is squeezing out van der Waals space. These are easy ways to see this. Let's talk about this first. So what are the intermolecular? Here are intermolecular potentials. These are calculated very well, and there are measurements to support these for 2 helium atoms, 2 neon atoms, for molecules. You have seen all of these. We approximate this by a typical Lennard-Jones potential, for instance, a 1/R6 attractive, a 1/R12 repulsive. We can calculate these. Everyone is interested in the attractive region of these potentials because that gives rise to the minimum, which is what holds atoms in a solid, like in solid xenon or in liquid xenon. But it also holds molecules. They're active between 2 benzene molecules. Here is a benzene crystal that I have worked on. And there are attractive van der Waals forces, dispersion forces. They're not that easy to calculate, but they can be calculated. And everyone is totally uninterested in the repulsive part of the van der Waals potential. That's often abbreviated of a, let's say, a Lennard-Jones potential. It's often abbreviated by 1 over R12. Some people are so not interested in it that they approximate it by a wall going straight up. Well, I've just finished telling you that under pressure, there are no walls. And under the pressures of a few gigapascals, you go into this diagram is deceptive because the attractive part and the minimum. What is the energy minimum of the dispersion force that holds two atoms or molecules together? It's of the order of a few kilocalories per mole for molecules and atoms. But the repulsive part, you can easily go into it for a long way. Let me give you an example. Here are two examples. So these are from calculations, but you can do the calculations pretty easy. The calculation at left is for silane. So what you see at the top is a model structure for SiH4 in which it looks like they're SiH pieces. No, these are not SiH pieces. That's a piece of another molecule that continues in the next unit cell. This is one unit cell of a structure with two molecules of SiH4 in a unit cell. And what you see here is a pressure on one scale, and on the other scale, the intermolecular H separation. And what I'm talking about is the non-bonded one between two different molecules. And what you see is it starts out in the initial structure at 3 angstroms or so. That's a van der Waals contact between two silanes, two hydrogens of non-bonded. That's the minimum of the van der Waals potential. You squeeze it, and it goes down, and in the first 10 gigapascals of pressure, look how much the HH distance goes down. Not a hundredth of an angstrom, but 1 angstrom. 1 angstrom, it goes down from 3.1 to 2.1 in 10 gigapascals. What you see at lower right is the same thing for H2 molecules. Now, this is solid H2, which is only available at low pressure, at low temperatures. These little dots here are not hydrogen atoms. That's a H2 molecule, which you're seeing from the top down on a diatomic. It's a projection, but the rest you see. And the distance I'm talking about is not the bonded distance, which you and all of your students know as 0.74 angstroms. It is the shortest contact from one hydrogen to another hydrogen of another molecule. It's the lowest non-bonded contact, and that's what's being plotted here. It starts at the 3.1 angstroms again, and in the first 10 gigapascals, it goes down to below 2. Do you understand what I mean by saying van der Waals space is most easily compressed? If you believe these numbers, and I ask you to believe them because they can be calculated well. When you squeeze something, you actually squeeze out not empty space, but the space of weak attractions. And only after you do that, do you begin to squeeze on the bonds, so to speak. That's just a colorful way of talking. Okay, so what's the second thing that happens when you squeeze some material? Just remember in this that there is one option that I'm not allowing you, and that a diamond anvil cell, which you subject to a pressure, is not allowing to the molecule. It's the option of making the volume bigger. Can only grow smaller. So what happens when you take two molecules and you squeeze, and the space gets squeezed out so that the hydrogens of one molecule come closer to the main group atom? They come closer to the hydrogens of the other molecule, but they also come closer to the main group. So here is something which you can say very easily and makes sense into an inorganic chemist. What you do when you increase the pressure next is you increase the coordination at the main group and transition metal atoms. Let me give you an example. You just saw silane. I just showed you a structure at upper left of silane, calculated at ambient pressure or higher. I've kept the pressure, but now I squeeze more. I squeeze to 200. And at that point, the hydrogens are close together, but also the hydrogens are getting close to silicon. And in fact, the thing rearranges. So this is what's going on, first of all, for things we've already talked about. Remember I told you that CO2 goes into a quartz structure? That's what's happening. Quartz CO2 is 2-coordinate at carbon and oxygen. Quartz is, of course, 4-coordinate in oxygen at silicon. So that's what happens. Nitrogen, the world's strongest bond, 10 eV in strength, or whatever that triple bond is worth. That's the atomization energy, the dissociation energy. At a high enough pressure, an analogous allotrope in which each nitrogen has 3 nearest neighbors is actually at a lower energy. And that 3-coordinate structure like that of phosphorus and silicon is what is favored. What is happening here is, this is the subway. The metro in New York is what I have a picture of. At low pressure, the number of nearest neighbors is 1. At higher pressure, it's 2. You go to next higher pressure, and you get to a situation. I have often ridden to the university in New York City at Columbia from my home in part of New York to Columbia, and I have learned how to sleep in this environment with 6 nearest neighbors. This is how life is. I just want you to know that there are some places around the world where, rather amusingly, this is the Tokyo subway. You notice that people are very orderly, lined up for get on a train, but once they are on a train, other people are hired to push them in order to provide a higher pressure inside the car for transporting, for mass transport. This is basically the sardine principle at work, but you get more nearest neighbors. You don't like it, or you do like it, but eventually you like it enough when it's against the cost of pushing away your neighbors. So here's what happens to silane. You remember the structure at 1 atmosphere? It has discrete molecules which are in an environment of other molecules. When you compress to about 200 GPa, you get 2 structures. One we found at Wright, one Pickard and Neitz found. And both of them, the silicon is 8-coordinate. So that's a little hard to see there. That's the silicon, the yellow. It is sharing 2 hydrogens each. Here you see 2 of those pairs with 4 different silicons. The alternative structure is 8-coordinate, where each silicon is sharing 1 hydrogen, that's the green ball, with another silicon in the middle of the next polyhedron. I knew this polyhedron very well because I had experienced in boron chemistry, and that itself tells you something about how to get prepared for this. So let me describe this in different words. Silicon has to form more bonds because that's the only way for the atoms to get closer to each other. It doesn't have any more electrons. It has the same number of electrons. How do you form more bonds with the same number of electrons? I experienced that in boron chemistry. I saw this in diborane. And in diborane, that hydrogen forms two bonds. Hydrogen doesn't really want to. They're not full bonds. They're electron deficient 3-center bonds. I know about that from boron chemistry. What I assure you is that very few physicists, if any, know about diborane and the bonding in it. So here you see the beginnings of what I mean by a chemical imagination under very tight conditions. Chemists actually have an advantage here in that forming more bonds than you can normally form is something that chemists have encountered. And here, the moment I saw the Pickard-Neat structure, that structure spoke diborane to me. It did not need to tell me anything. I saw it because I knew diborane so very well. Okay, increased density with increasing pressure leads to higher coordination. You get more bonds, full or partial, with the same number of electrons. Remember, why same number of electrons? Because it's the same number of atoms that's being squeezed into that space. And that leads to multi-center bonding, electron-rich and electron-poor. And to anyone who has seen a beautiful endpoint in borane chemistry, the icosahedron of B12H12 2-, or who has seen PF5 with its axial electron-rich 3-center bonding, anyone who has seen B12H12 2- has no trouble imagining Aramets and Hamleys hydrogen polyhedra in this lanthanum H12 structure. They don't seem so strange. Put it another way, that's what education is about. Education and science are about things, making things less strange than they seemed at one time. And that's what's going on in here. Oh, I'm going to skip that. Okay, we squeeze more. When you squeeze more, you decrease next the bond lengths of covalent bonds, and you decrease especially the size of anions, because anions are puffy with electrons, and those electrons are squeezable. And eventually, we are now approaching a place where the chemical experience begins to fail us. We enter a new world of electrons moving off their atoms. Still carries us for a while. I'll show you one piece of that world. And we enter new modes of correlation. But in the beginning, it's rather interesting how especially increasing coordination is very chemical. But electrons moving off their atoms, I'll show you, is also chemical. But let me show you things that just so that we teach our students, but we really haven't kept up with the world. So here's a piece of news. For all the alkali metals and the alkaline earth metals in groups 1 and 2 of the periodic table, their crystal structures at atmospheric pressure can be described in terms of what we do teach our students in beginning chemistry. And that is, they are close packed structures, which are either hexagonal or cubic closest packed, or occasionally body-centered cubic, which we could talk about, which is close to close packed. But for every one of these, as you increase the pressure, in the last 25 years, we have learned that they go out of the close packing into some other less symmetrical structure. And in the spirit of not teaching our students the complexity of the real world, we don't tell them about this. Maybe because we don't know about this. But let me give you an example: barium and rubidium. Barium at 1 atmosphere is body-centered cubic. Barium metal, this is barium metal. Just at 5.5 gigapascals, I can't see it under here. Let me just, at 5.5, I'm just going to go, no, I'll stay. It goes to a less symmetrical structure. It goes to some other structure. I can't read it under my screen. At a still higher pressure, barium 4, as it's called, there are given Roman numerals, goes into a structure which has been solved with 288 atoms. I don't even know the space group in a commensurate unit cell. I want you to think about this. This is not a compound of barium. This is just barium. Why is barium doing this? Going into a structure with 288 atoms in a unit cell. That's what you'd expect an intermetallic to do, but not barium by itself. But it does it. And I'll show you at least one possible way to start thinking about this. Here's another one: rubidium at 17 gigapascals. That is, 17 gigapascals is just 170,000 atmospheres. Not even a million atmospheres. It goes into a structure where part of it looks like a clathrate. That's the green atoms, the rubidium atoms, which are numbered 1. And threading that clathrate-like structure is a needle of rubidium-2 atoms, which has an incommensurate cell spacing relative to the green. The blue lattice is incommensurate with the green lattice. Again, why are they doing this? Well, I don't know exactly, and I did not predict it, but actually some other people did. The first suggestion of something, I want you to see how radical this suggestion was when it was made by Neil Ashcroft in 1999. He did it for elemental lithium, and he first predicted that under lithium, which is, I think, BCC, but FCC is not far away, under atmospheric pressure, when you compress it, goes into a structure which you can see what it is. You can see 2 lithium atoms. And then there's a relative depletion of electron density. That's the yellow and red. And there is electron density in between the lithium molecules. So what it gives is a Li2 plus electron minus, a structure which I would call an electride, and which I knew from work of Jim Dye at Michigan, and I knew about electrides. So what happened to elemental lithium under pressure, that was the theoretical prediction. It wasn't right, but actually there was a modification of it. Generally, it was okay. Electrons went into the lattice in between, and there was formed a kind of Li2 molecule here, but strongly connected to the next one that was found experimentally in Scotland. I want you to imagine how strange that prediction looked in 1999 that lithium was not a simple structure. So let's talk a little about space filling and why this happens. Okay, here we go. It did not take scientists to teach people what is the most efficient stacking in 3 dimensions of spheres, of hard spheres. Grocers from prehistoric times piled their fruit up in layers like this, and some of them actually recorded that there are several ways to do this. You see at the bottom 6 around 1 and then 3 on top, but then the next one has a choice for where it goes. So the packing of identical spheres, this is a problem we give to our students, maximizes at 74%, and is something which we've known for a long time. People actually knew and that if you applied pressure, this was no longer true. And so here is a book by an early book of agricultural chemistry by Stephen Hales in 1727 is when it was printed. When it was written, the book 1761 is an owner has scribbled on it. It has a wonderful title about vegetable statics, or an account of some statical experiments on the sap in vegetables, being an essay. It goes on. And then what he says, he did an experiment. What he did is he took some fresh peas. The writing here, the orthography in English was not settled yet around 1727. So it's like Russian, which could be written in a number of ways, and German too. So what he took is took some fresh peas, put them into a big pot, put a lid on a pot, put different weights on it. This is primitive high pressure experiments, putting on weights of 1,600, 800, and 400 pounds. And he says, though the peas dilated, they did not raise the lever, meaning the cover of the pot, because what they increased in bulk was by great incumbent weight pressed into the interstices of the peas, which they adequately filled up, being thereby formed into pretty regular dodecahedrons. Okay, let me translate it into English. What he's saying is, if you take spheres and if you compress them, the spheres, the peas are not stupid, not as stupid as the people around them. And what they do is even though they fill up 74% of the space, you are making them compressing more. So of course they go into the empty space between the spheres, and in a process change shape. Spheres are not the best way to fill space. Turns out you can, this is some fun physics done by a friend of mine at NYU, Paul Chaikin. He showed that you can fill up with spheroids with elliptical spheroids of revolution, with a certain kind of departure from the sphere, you can fill up more of space than spheres fill up. But in general, spheres of different size can pack more efficiently than spheres of identical size. It's obvious. After you've formed a 74% packing of identical spheres, you have 26% of the space left over. So if you had small spheres, you could pack them in there. Okay, so actually this is a mathematical problem. There's a wonderful paper by Stillinger and Torquato about binary sphere packings with the mathematical problem of how to pack space with 2 spheres of different size. And there are a number that are more that are more dense than the 74%. What does that have to do with chemistry, you will ask? So, how do you get, supposing you have two spheres, like rubidium or barium, and they are of a certain size, and you think they pack in a certain way. How can you make them different from each other? And actually, if some of them become negative, you think they'll be bigger. And if some of them acquire a little bit of a positive charge, they'll shrink, become smaller. So it could be that by partial electron transfer from one rubidium to another, you might get a better packing. That can give you at least a way to think. There is nothing more chemical than I can think of, that a cation is of a smaller size than an anion, given the same number of electrons. So this is a very, very chemical thing. There's more. I want to now justify actually the title of this talk, The Chemical Imagination at Work in Very Tight Places. Very tight places is just a colorful way of saying high pressure. The chemical imagination at work is what is behind my recognizing diborane in the silicon H4 structure. It is behind coming up with a way of thinking in terms of ion sizes about the weird rubidium packing in elemental rubidium. It is behind my thinking of higher coordination. Just the fact that I know that that tin tetrafluoride crystal structure has in it octahedral coordination of tin, and that I know that tin is below silicon in a periodic table. Those are very simple chemical things. I am not talking to you about complicated things. I'm talking about introductory chemistry and simple ideas. And in some way, what I've done is I've given you a justification for teaching introductory chemistry. These things, if you hold on to them, if you really examine what they are about, they are a story about which gives you a lot of work. Let me just go back to NaCl3, which you see at the top here, and NaCl3. And I want to tell you the difference of a chemist and a physicist approaching this. Supposing someone told you that you had Na3Cl and that you also had NaCl3, how would one think about this? So the physicists are not stupid. They know that sodium chloride is Na plus Cl minus in an ionic lattice. They can calculate the Madelung energy of that lattice. So when they see Na3Cl, they see maybe it's NaCl plus maybe it's NaCl plus Na2. Okay. And then they say, I will transfer one electron from one Na plus over to another chlorine, and I will have an Na plus and two Na atoms. And what will those do? So they'll come up with something. If they see NaCl3, they will say, I'll take an electron from the sodium, transfer it to a chloride. Now here is go back to Na3Cl. Here is the difference between a chemist and a physicist. Perhaps I'm making too much of it because I want to, of course, I want to praise the chemists. That's my life. I'm doing it I'm praising the chemical intuition. Here is one thing which a chemist in an introductory chemistry would not do. Knowing that sodium is sodium chloride, Na plus Cl minus in an ionic lattice. When he's given Na3Cl, and asked to postulate what it is, he would write Na plus taken 3 times and a chlorine atom 3 minus. I think we have taught our students not to write a chlorine 3 minus. That would fill the next shell. Chlorine minus is perfectly okay. It's like xenon, but not xenon. It's like argon. But we know something. The same way, take NaCl3. You take an electron from sodium, you put it on one chlorine and you have a chlorine minus, and then you have 2 chlorine atoms. So you have a chlorine minus and a chlorine 2. Now, if your chemist knows something about inorganic structural chemistry, they will know that at 1 atmosphere, not to speak of 100 gigapascals, a chlorine minus next to a chlorine molecule is not going to remain there, but to form a trichloride ion, just like the familiar trifluoride ion, a nice linear array. And if you look at the structures of these things, you find in them also arrays like this. Okay, I haven't given enough time to study of these things, but what I think I have made clear is that when you look at these molecules, if you use the full extent of your chemical intuition, which means knowing all of organic and inorganic chemistry, and it was given to me by the fates that I had to go through and enjoyed going through all of organic and inorganic chemistry, and was not scared of solid state chemistry, and in fact could teach people how to do it. When you know these things, the bonding that you get, even under extreme conditions, which are way far away from normal, can still be approached by starting out with some chemical intuition. Thank you for letting me tell you the story.
Thank you very much for your lecture. Something like alchemy. Dear colleagues, do you have any questions? Our lecture.
Very interesting lecture and very nice stories for students of first year that they might understand that structure is very independent from pressure. It can imagine absolutely new structures which about they don't think in the school about it. You must open eye for them in the first year of the university.
Yes. Chemistry is very rich, and I had to work very hard to reach a degree of collaboration within condensed matter theory with Neil Ashcroft to be able to get chemists to listen to us. But there's in part our education is very different from the physicists. I just want you to know how I don't want chemists to feel inferior when they meet with physicists. We often feel that on a basis of mathematical things, but it is so, we know it is true there are things we have to learn, but we know so much as chemists.
Okay, Alexander, please. You have a question?
Thank you for this wonderful lecture. You open a new angle of science. I think we have never met before.
Yes.
We have never think about these points before. And I have one question. For example, everybody know about the Baryk process in, for example, in gases. Yeah. But what happens in a solid state? When you apply such huge pressure to your solid material, you must, no, you will get isolation, huge amount of energy, yeah, when you apply this pressure. And what happens with this energy? And what is interesting, second part of this questions, what happens when we return our solid material to normal pressure? For example, for gases, they widen and consume energy. But what happens with solid?
Yes. So let me answer the second question first, out of some personal experience. There is energy released when you return to atmospheric pressure. And how to get rid of that energy is a real problem. I had one personal experience which early on, which did not involve high pressure, but involved a temperature conditioned increase in volume. So let me tell you the story. I was working in the summer as an undergraduate at National Bureau of Standards in Washington. And I was doing some experiments with someone about acetylene chemistry. So just acetylene, HCCH.
Mm-hmm.
And we were transporting the acetylene from one part of a Schlenk tube apparatus to another one. We had it in a glass vessel that was linked to the apparatus, and we transferred it to another one. And we did this using a usual way, a liquid nitrogen dewar flask under the glass vessel that condensed the acetylene in one, and then I wanted to transfer it. I put the dewar in another part and wanted the acetylene to flow. The mistake I made at age 19 in this laboratory was I took off the dewar rapidly and put the other one on. What happened next was a little explosion. It was little, thank God, because I did not have much acetylene there. But what happened was the solid acetylene went to liquid to gas. And it was known by the people working with it to do this slowly because the fracture of the crystals of acetylene as it vaporized was sufficient to sometimes generate enough heat to get the acetylene to burn. So I didn't know that. So you have to take off the pressure very slowly in these things. Otherwise, you will get mechanical damage to the crystals, and you will not provide pathways for the gas to go off. Okay, to the first question is you do supply. So work comes in many different ways. and work, and therefore energy, is supplied to in a diamond anvil cell, and it is taken up by the strength of the diamonds and the metals around them as a decrease in volume. So work is delta PV, and so it's taken up as a delta V. But when you go back, and if you were to when you have this material, you have to have the energy somehow dissipated in collisions to the walls and I don't know exactly what they do, but this is a very good question. This is a little bit connected to the chemistry in interstellar space of ions, like H plus H2 is energetically downhill to give H3 plus in interstellar space. But unless you have a third body to take off the energy, you will not form H3 plus. It'll fly right apart because there is nowhere for the energy to go. So you have to have some sort of energy balance. Usually it's vibrations of the lattice that take up the heat.
Thanks.
Okay, thank you. Igor, please.
Professor Hoffman, thank you very much for this wonderful talk. It's really amazing how imagination can help us in understanding what's going on under high pressure. And what about experimental data? You promised to tell us how the temperature is measured, or how these data you exemplified were experimentally confirmed. You said also that UV is not useful. Can you tell a little bit more about experimental measurements under high pressure?
So,
thank you.
First of all, how does one measure the pressure in there? So, this is very clever, and it involves some chemistry. So, the way that the pressure is measured, this is not something, it's something that happened by accident, was then exploited, but it has a very chemical side. It's measured by putting into the diamond anvil cell. So what one does is one begins by taking a metal plate, as I understand it, and you drill, and the metal is from some hard metal, like rhenium, perhaps. And then one drills a hole in it, a small hole. And then one buys, and this is experimentally expensive, diamonds which have been grown or polished to expose a certain flat area. One then puts one diamond from the top, one from the bottom. That's the general. And then puts that into this metal cell, and then the filling the cell and treatment of the cell has much chemical complexity in it. The pressure is measured by adding it depends on the pressure range, but in the range of 1 to 3 million atmospheres, in the range of where interesting things happen, it's measured by adding a small crystal of ruby to it. The crystal of ruby has in it an electron. It is red, but it varies in color. And the color is an indicator of the pressure. Okay, that's easy to say. This is calibrated with other things. This is like science anywhere. You don't believe numbers until you calibrate them with another measurement. But the transition that's involved in the color is a D to D transition, I think, of the chromium ion in the ruby. So it is very chemical. So what you are doing is affecting the crystal field splitting, T2G and EG, which we teach our students, in an inorganic octahedral crystal field. I think it's very nice that it's chemistry that's giving us that measurement. That splitting is affected. Why is it affected? Because the oxygen atoms are coming closer to the chromium, whatever is going on there. Okay, now, how does one measure the temperature? That, as I understand it, this is a really difficult problem. They don't have a good way of measuring the temperature. They can heat the thing, but they do so, they can heat the diamond anvil cell within a small temperature range. But that temperature range of 100 to 200 degrees C is not enough to cause some of the activated transitions that they want to happen, like to cause an N2 molecule to go into a three-dimensional nitrogen lattice. And for that, what they do is they shine in a classical, I think, YAG laser in there, but they don't know. It's a non-equilibrium process. They don't know what the temperature is, and I think they need ways to do this. Raman is done because they can get a Raman spectrum off a laser beam that goes in there. UV is not useful because it is useful. The closer you become to metallic, if you have a transition that's near, it'll move into the visible. So you can tell reflectivity, or you can tell optical properties from the UV, but as I understand it, but in general, how useful is UV for organic structure determination? I mean,
right.
it's useful in places.
Much.
Yes. If the thing is colored, you can do it, but if it's not colored, you don't have much to work on. But Raman is so interesting because it gives you information about vibrations over a wide range of the molecules or the lattice. I think I'm not an experimentalist, so you will have to ask some of the specialists in the area.
Thank you very much.
For more detail.
Thank you very much. We have two questions in our chat. What would happen to a non-stoichiometric compound?
Often the mixtures that are put in there are non-stoichiometric. You know, in some ways, this is so far away from stoichiometric chemistry.
Yes.
As you can imagine, and very often, I mean, just imagine, they didn't know, Erametz and his group, that this superconducting structure that they were after was SH3 in a rhenium trioxide crystal structure, a very specific crystal structure. What they did was they filled the unit cell with H2S, which did not please the physicists because it created a bad smell, and with H2. But they didn't know which should be in excess. They tried everything. And in the end, sometimes you want to generate the reagent in situ. So one of the ways that the Hemley group found successful in making LaH10 was not to take LaH3 and H2, but to take LaH3, or to take even lanthanum metal, and supply the hydrogen from an external source, which was aminoborane, NH3BH3, which when heated up expels H2. It seems it was not something they planned, but they are experimentalists. They are this is what I like when I get to talk to these people. What they actually do is they are doing typical exploratory synthesis with no clear idea what they will get.
Mhm.
Oh, they pretend they know what they're doing because they're physicists, but it's in their job definition to understand, but they don't. They pre-treat the cells, they modify things. They are in the land of the, if not irreproducible, the moderately reproducible. When they are successful, they have trouble because they have trouble reproducing what made it successful. It's not an untypical situation for chemists as well. The payoff of making a room temperature superconductor is very large, but I think they are basically doing chemistry. And as I've gotten to know these people, I've gotten to get them to appreciate little guidelines which help them chemically to understand the things that they are doing, so that they get little pieces of understanding. It's very interesting, this interaction. I have enjoyed it immensely.
Okay. Well, Valery, please, you have a question.
Oh, I would like to ask, well, first of all, thanks for the lecture. And I'd like to ask about the part where you told us about oh my God, like for example, sodium becoming non-conductive, and then becoming
Yes.
conductive again. You had a little picture with electronic orbitals that was not very clear.
Yes, I did
What
not
what does
explain that.
depict?
Yes, what you're asking, what happens? How does sodium become? So here's what happens. So what happens is sodium metal becomes an electride. It becomes Na plus electron minus. So now you have to know a little bit about electrides. They are an unusual state of matter where you get electrons off atoms and in space. And these things are known in some chemical things, but there was one chemist, Jim Dye, spelled D-Y-E, who was an expert in these and was very good at synthesizing these. This is at ambient pressure, but what you need to do is to provide a place for a lot of driving force for the sodium. This is under ambient pressure, for sodium to go to Na+. And this happens by providing what Jim Dye did was he took sodium with a what are these called? I'm having a moment where I've forgotten the terminology. One of these places which take a sodium ion. They have a lot of ether oxygens around this. I've forgotten the name of the compounds. Maybe somebody can help me. If you have one.
Crown ethers.
Yes. These are things with rings and with oxygens, and they bind the Na+, and then the electron goes in a hole around it, and you have to prevent there being anything that is reducible by the electron. That is, if there's a place for the electron to go, it'll go there. So some organic chemists have used Birch reductions and other ways of communicating electrons to things, where they remove the electron off a lithium and then transfer it to an organic molecule. Then we have also KC8. This is a graphite intercalation compound, but it can be used as an organic reagent. So what happens when you squeeze on the sodium is the sodium atom outer electron is in a 3s orbital. It is rather exposed, and the effect of pressure is to raise the energy of that s electron, so it becomes easier to ionize it. So, but where does it go? Well, it turns out that the space between the atoms is in principle has energy levels and could provide a home for that electron. Think of it as a particle in a box with no atom in it. And that's the electride. It's Na plus E minus. But Na plus and E minus has states which are in the ultraviolet. And this is also related to some of you who may know the chemistry of lithium ammonia solutions or of the hydrated electron in radiochemistry. An electron goes off the lithium and is trapped by ammonias, by the dipole moments of the ammonias around it. Well, this electron in sodium under pressure is trapped in the interstices of the lattice. And it forms I've forgotten now what kind of lattice. I think it's a nickel arsenide lattice with the sodium pluses and the electron minus, but they are both don't have a transition and are visible. And that's why this is transparent. Then you squeeze some more and it becomes metallic. The areas where the electron is begin to overlap with each other. So what you have there is metallicity due to sodium ions in a sea of electrons, essentially, which are all off atoms and connected to each other.
Nice.
Does this make a little bit of sense?
Am I getting this right? So at like medium high pressure, it becomes sort of like a crystal of sodium plus ions and just electrons?
Yes.
Is it? Wow. That's
Medium is
wow.
medium is 1 million atmospheres. It's not a few. So I would need to take you through stages. One of them stage is what happens to the ionization potential of a sodium atom as you apply pressure to it. And I would have to convince you that a 3s electron is affected more than anything else, and that the ionization potential of sodium, which anyway is only at a few eV, is decreased as the ionization potential is decreased as you increase the pressure. But I can send you some things more on that, but I think for now this.
Wait, sorry. Didn't you say it? The ionization. Sorry. The ionization energy decreases and the potential increases, right?
Yes, it takes less energy to knock off an electron from a sodium atom under pressure or from sodium metal than it does without the pressure, for either the atom or the metal. Both of them lose an electron easier under pressure.
Well, that's really interesting, you know, a little bit unexpected because of this like core notion when you apply pressure, stuff becomes more compact, but not on the one atom scale like this.
That's right. It's got not on a one atom scale, so it's all relative. So yes, the core notion would make you come closer together, but at some point it becomes too costly. Let's see. Here's another simple way that I could tell a student. I would tell a student that if they knew quantum mechanics, that a sodium atom is 1s squared, 2s squared, 2p6, 3s1. Okay, so that 3s1, the valence electron of the sodium, is gotta stay orthogonal to the 1s electrons of the sodium. They are both spherically symmetric, and the 2s electron has to stay away from the nucleus more than the 1s electron. And now, as you squeeze, that begins to exact a price. That is, it keeps the electron out where the squeezing counts more, so to speak, so that the effective pressure the 3s electron is under is a combination of an internal pressure from the 1s electron that's underneath it, and that it has to stay quantum mechanically orthogonal to, and the outer pressure, which you can visualize in a number of ways. And so at some point, it is very unhappy, that 3s electron, and it jumps over to some other place in the lattice where there's more room for it. And you gain some Madelung energy back when you make sodium plus and electron minus, but that's not the whole story, Madelung energy.
Can I also ask, there was one more pretty unexpected thing, if I understood it correctly. When you were talking about You said something along the lines of weak attractions, like weak bonds, like the distance decreases first, like not the. Do you understand this correctly? Like imagine like two particles or just a box filled with some particles that have a weak force acting between them. Does the okay, sorry, I kind of
Now
can't.
it's hard to formulate. I
Yeah,
did
sorry.
say something. I initially molecules and atoms and matter in general exert weak non-electron pairing, but quantum mechanical forces, dispersion forces between them. They are weak, and they can be easily overcome if one needs, if thereby one gains some volume. So that's another way to think about it. The work goes in through P delta V. The volume change is first taken up by matter by getting the atoms closer to each other. And we think that when we get atoms that are the first atoms that come closer to each other are not the ones bonded to each other. It's the space between the molecules, between the atoms. And that's why it's so dramatic for molecules. That's why I showed you that picture of SiH4 and H2. And you could see that all it took, 100,000 atmospheres, much more than the Haber-Bosch process. But when you put in 100,000 atmospheres, two SiH4 molecules would come together so that they are 1 angstrom less apart. There are many ways of saying it. I would push the two SiH4 molecules into an uncomfortable position from the point of view of a van der Waals dispersion interaction. I would push them into the repulsive region, but the repulsion is not as much as I would, as P delta V would be, as I would get back from a P delta V change. I had to get used to this world where the energy was, volume changes were involved. But we have also done some things which are relevant to organic chemistry and which are, you can see a paper we have in Angewandte Chemie about 8 years ago about the effect of smaller pressures on the activation energies of organic reactions. Let me give you an example. A Diels-Alder reaction, if you are an organic chemist, of butadiene plus ethylene to give cyclohexene. That's a reaction which goes down in volume. The composite molecule occupies less volume than the reactant. You can be sure that the effect of pressure will be to advance that reaction, and it'll advance it in two different ways. It'll advance it is a very loose word. We'll make that reaction easier. It'll both increase the exothermicity of that reaction and it'll decrease the activation energy for that reaction, both because the transition state and the product occupy less volume than the reactant. So you can reason about it this way. And there's nothing new in this. This has been the work of a very good chemist, Lebel, over the years. But our papers in Angewandte Chemie can talk about it. Okay, I think
Yeah, I think, yeah, Roald, thank you very much. I think it's time to finish our discussion.
Yes.
Yeah,
Let me just say some final words that we are, that I myself and others are, of course, aware of the struggles that you are undergoing under Russian aggression. The keeping a sane scientific presence, learning about things, teaching the next generation is extremely, extremely important. The light of freedom, in a way, shows up in so many ways, and one of them is in the freedom of the mind that we have to explore new chemistry. That's in part why I didn't feel guilty at all about telling you about some chemistry which is known to physicists but not so well known to chemists. Anyway, I understand, because of having survived World War II as a child in that region, just what war means. And so I wish you well, and I wish you strength.
Thank you very much.
Thank you. Thank you very much.
Thank you.
For your support, and thank for your time and very wonderful lecture. And I would like to say I've been enjoying today during our seminar.
Yes, good. Good to talk to you. Valentin, we'll be in touch.
Be in touch. Thank you. Have a
Yes.
nice day.
I'll stop sharing and I'll go.